Today we're going to look at a string of increasing growth of certain sequences that gives you a feel for what types of sequences grow much faster than the other. And so this string of inequalities is something that I showed in my Calculus 2 class. We prove a couple of them, but really it's just good to get an intuition for when one thing grows much faster than the other. So this is the string of increasing growth that I talked about. So down here at the bottom are power functions. So like polynomials or like n to some exponent or x to some exponent. And then much larger than those are exponential functions like 2 to the n or 2 to the x or e to the x or 3/2 to the n, so on and so forth. Above that are factorials like n factorial or even other descending products like double factorials and other generalizations. And then at the top are super exponentials. Those grow faster than anything else on the board. Of course, you could concoct something to the right of that grows even faster. And so, well, what do I mean by this increase in growth? Well, I mean that if I take something to the right and something to the left and I form a quotient where the object to the right is in the denominator and then I take a limit, I should get 0. And that's exactly what we'll show. So I've numbered these inequalities 1, 2, and 3, and we'll do each of them separately. So for this first inequality, I'll take an exponential function, I'll put it in the denominator. I'll take a power function, I'll put it in the numerator. And then if the exponential function grows much faster, then my limit should be 0. But I need a couple of rules here. I need the base of my exponent to be larger than 1. And I need my exponent on the power function to be bigger than or equal to 0. So of course, if those are not the case, we could do some manipulations to put them in this form. Okay, so this is the limit that we want to show. And we're going to do this via the squeeze theorem, essentially. So let's take some natural number, which I'll call m, such that m is bigger than or equal to r. So for any positive real number, I can always find a natural number that's larger than that positive real number. That's technically known as the Archimedean principle. And then we're also going to take a real number b, which is bigger than 0, such that a can be written as 1 plus b raised to the m power. Okay, so that's definitely possible as well. If a is bigger than 1, then a can be written as 1 plus something. Then you essentially just take the nth root of something involved in that, and you get this possibility right here. Okay, so now that we've got this set up, I'm gonna form a string of inequalities. So let's start down here at the bottom with 0. And 0 is going to be less than or equal to n to the r over a to the n. So that's essentially the sequence that we're investigating here. But that's going to be less than or equal to n to the m over 1 plus b to the m times n. So the replacements that I've done here are m for r. M is bigger than r, so we just made the numerator larger. And then I replaced a with 1 plus b to the m. I kept the denominator the same. So if the denominator stays the same and the numerator gets larger, well, then of course the whole thing is larger. And that's exhibited in that inequality. But the reason I chose b so that this would happen with this exponent of m is so that I can factor out an exponent of m for this whole term. So let's do that. So this is going to be equal to n over 1 plus b to the n power, all raised to the m power. Now I'm going to perform a binomial expansion in the denominator. So this is going to be equal to, so I'm going to keep this whole thing within this mth power. So this will be 1 plus n times b plus n times n minus 1 over 2 times b squared plus more terms, where those more terms are from multiplying that out. We could write down exactly what that is, but we won't need it for our purposes. And then this is all raised to the m power. Okay, so now earlier I manipulated the numerator and created something larger. Now I'll manipulate the denominator and create something larger. But in order to do that, I need to make the denominator smaller. And I can very easily do that just by leaving some terms off. So let's leave off these first two terms, 1 plus nb, and this plus more terms. So that definitely makes the denominator smaller, which makes the whole thing larger. And then we're left with this. So we have n over, so now this will be, let's see, n times n minus 1 over 2 times b squared. And that's all raised to the m power. But now we can do a bit of simplification here. This is going to be equal to, let's see, we'll have 2 over b squared times n minus 1. And then that's all raised to the m power. And notice some stuff canceled, like this n and this n canceled, but I think we're good to go there. And now let's take the limit of this object as n goes to infinity. But it's pretty clear what's happening with that object as n goes to infinity, because the denominator is getting larger and larger and larger and larger while the numerator is staying the same. So that means this limit is equal to 0. So let's see what we've done. We've pinned our goal sequence between the constant sequence 0 and a sequence that tends towards 0. So by the squeeze theorem, that means we have this limit right here. And so that means we have indeed established this, growth inequality. Okay, now let's move on to the second one. Okay, so for the second inequality, we want to show that factorials grow much faster than exponential functions. So let's take an arbitrary exponential function, a to the n. We'll take a to be bigger than 1. And then we're going to put that on top of a factorial. And we should have this limit equaling 0 if the denominator is indeed growing much faster than the numerator. Okay, so let's see how we might do this. So we're going to do the same game with an inequality in the squeeze theorem. So let's find some natural number m such that m is bigger than or equal to a. So again, a is a real number that's bigger than 1. We can always find a natural number larger than a real number. Again, that's by the Archimedean principle. And now we're going to set off our inequality argument again. So let's pin everything below by 0. So we have 0 is less than or equal to a to the n over n factorial. But now that in turn will be less than or equal to m to the n over n factorial. So we're kind of doing a similar trick to before. Here we change the numerator to make it larger by our choice of m right here. Okay. Now for our next inequality, this is only going to hold when our n is large enough. So let's point that out here. So this is going to be less than or equal to, and this is only when we have n larger than m. So n is the variable here. M is just something that we have fixed as a constant natural number larger than a. So only when n is bigger than m do we have this inequality. But that's totally okay because the limit is as n goes to infinity. So for most of the n that we're talking about within this limit, those are larger than m. Oh, but let's also use the fact that when n is bigger than m, that means we can write n as m plus k for some natural number k. So I think that's pretty obvious. And so now let's just write what we have here. So we have m to the m plus k over m plus k factorial. Great. I guess this is technically an equality here, but this is an equality that really only holds when we have n bigger than m, because that's the only time we can write this, in this method. Okay, so now I'm going to separate this into pieces, and those pieces will help us build our inequality. So the pieces will be as follows. I'll have an m to the m power over m factorial. So those are the first m parts of the products of the numerator and the denominator. And then I'll have an m to the k over, well, whatever it takes to build m factorial up to m plus k factorial. So that'll be m plus 1 times m plus 2, ending at m plus k. So notice that there are k terms in the numerator and the denominator here. Whereas this m to the m over m factorial is in fact just a constant in this case, because we've fixed m over here. So maybe we'll call that constant something. Let's say that constant is equal to c, and we'll do that in this next equality. So we've got this constant c, and then I'm going to split this up into, k fractions. So the first fraction will be m over m plus 1. The second one will be m over m plus 2. The third one will be m over m plus 3. I think you can see where we're going. The last one will be m over m plus k. And now here's where we're going to start introducing our inequality again. But now we're going to manipulate the denominator. We'll make the denominator smaller, thus making the whole thing larger. And we'll do that by exchanging m plus 2 for m plus 1, m plus 3 for m plus 1, and so on and so forth. So in other words, we're going to replace all of the denominators except for m plus 1 with m plus 1. So that makes all of them smaller, thus making the whole thing larger. So now we've got this constant, and then we'll have m over m plus 1. Well, actually a bunch of copies of m over m plus 1. How many? Well, there are exactly k of them. But let's recall that m was a constant, so that means m over m plus 1 is a constant, but in fact it's a constant less than 1. So let's point that out here. So this is a constant. I mean, it's a constant that's built out of our argument over here, but it is a constant. And furthermore, it is between 0 and 1, not including 0 or 1. But now let's let, well, our original variable n go to infinity, which is equivalent to letting k go to infinity, because we've got this relationship between n and k. But if we've got something that's less than 1 and we keep raising it to larger and larger and larger powers, its limit will be 0. And so now we've done the same thing. We've taken our goal sequence here and we've pinned it between 0 and something whose limit is 0. So that means by the squeeze theorem, we've established this inequality right here, which was our goal. So that takes care of this second growth rate problem, that factorials grow much faster than exponential functions. And now let's do the last one. Okay, so for our last inequality, we'd like to show that super exponentials grow much, much faster than factorials. So that means if I form a quotient with a superfactorial in the denominator and a factorial in the numerator, well, its limit should be 0. Well, what do I even mean by a superfactorial here? Well, this is just a word that I came up with, but I'm sure lots of people have come up with it for this kind of object. I don't know if it's standard though, but it is n to the n power. So we've got a variable in the base and the exponent. And so it's a classic maybe calculus 1 or differential calculus problem to find the derivative of x to the x. That's when you're doing logarithmic differentiation. So that function is like a continuous version of this right here. And in fact, it grows crazy quickly. Okay, so let's see how we might do this. Again, we're going to do the same sort of inequality argument here. This one is actually probably the easiest. So let's pin everything below by 0. We've got n factorial over n to the n. And then let's expand all of this out. We have 1 times 2 times 3, ending n minus 2, n minus 1 times n. So there's n factorial. And then in the denominator, we've got just a bunch of n's. So we've got n times n times n, all the way up n times n times n. So something like that. So notice we get a little bit of simplification immediately. Notice that this n over n will cancel. And then after that, I'm going to do some grouping. So let's group this n minus 1 over n, this n minus 2 over n, down here this 3 over n, and this 2 over n. And I guess that 1 over n as well. And then we'll make the observation that everything here is less than 1. And that's because, well, for n large enough, and of course, like n will be large enough here because we're ending both of these at n, we'll have the numerator less than the denominator. So let's write this out. So all of these are, well, let's be careful about it. They're between 0 and 1. So if we just replace all of them with the number 1, we build an inequality. So this is going to be less than or equal to, well, what's left over? This 1 over n here. I just replaced everything else with 1. But that very clearly has a limit of 0 as n goes to infinity. So just one last time, we've pinned our goal function between 0 and a sequence that clearly limits to 0. But then by the squeeze theorem, we have exactly our final result. And we have proven this last growth rate inequality. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.